Hey everyone, welcome back. Hope you have watched the previous video, because we learnt why we call logic gates as basic building blocks. We also saw number of transistors together form a logic gate. The transistor works as a switch, which in turn makes logic gates to work like a switch. We also saw when it comes to logic gates, we deal with only 0 and 1, also known as binary numbers, where 1 is on state and 0 is off state. When the input signal 1 is given to the logic gate, the gate is on. The signal passes through the logic gate, and we get the desired output. But if we give 0 as input signal, the gate is off, the signal does not get processed, and we won't get any output. There are some operations or functions performed inside the gate according to the design logic. The logic gates can have one input or more than one input. It depends on the circuit we are designing, but the output is going to be only one. So we can say logic gates are basic building blocks of a digital circuit that performs a logical operation on one or more inputs to give a single output. How are we going to define the functionality or operation a gate is going to perform? Well, we have truth table, Boolean expressions, waveforms or timing diagrams, and logic diagrams. Truth table is a logic table which shows outputs for all the combinations of input. Do you remember mathematics chapter permutation and combination? We saw questions like if there were 2 red balls, 1 blue and black each, how many combinations you would get if you had to pick 3 balls with at least 1 red ball. Confusing, right? This is why we write truth table. It shows all the combinations of inputs for any gate with only ones and zeros. For one input gate, we can either give 0 or 1. For 2 input gate, we have to consider all the combinations of 2 inputs. We will keep input 1 as 0, and for input 2, we can either give 0 or 1. So we can write it as 0, 0 and 0, 1. Next we will keep first input as 1, and again input 2 can be either 0 or 1. Therefore, we can write it as 1, 0 and 1, 1. We got total of 4 combinations. For 3 input gate, there will be combinations of 3 inputs. We will keep both I1 and I2 as 0. I3 can be either 0 or 1. We get 2 combinations, 0, 0, 0 and 0, 0, 1. Next we will change I2 to 1, keeping I1 same. Again I3 can be either 0 or 1. We get 2 more combinations, 0, 1, 0 and 0, 1, 1. If you observe, the inputs I2 and I3 make a combination similar to 2-input gate, with extra input I1 kept as 0, which means we can repeat the same 2-input combinations, but this time changing the input I1 to 1. Therefore, we get 4 more combinations, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Total of 8 combinations from 3 inputs. Did you see that when we had 1 input, we got 2 combinations? For 2 inputs we got 4 combinations. For 3 inputs, we got 8 combinations. We can make a formula to find the number of combinations out of this logic. That is 2 to the power of n, where n is number of inputs. Let's verify. For 1 input, n will be 1. We get 2 power 1, which is equal to 2. For a gate with 2 inputs, we get 2 power 2, which is equal to 4. We got 4 combinations here. For 3-input gate, 2 power 3 is 8, and we got 8 combinations here. This is to find the number of combinations. As for the combinations itself, The first input to the right will be alternate 0 and 1. The next input will be double of that, 2 zeros and 2 ones. The third input will be double of second, 4 zeros and 4 ones. Guess what the fourth input will be? It's 8 zeros and 8 ones. Easy, right? Next we have Boolean expression. It's a logic expression which evaluates or checks the conditions or inputs to give either true or false state. For example, if we have input A and B, output Y, the expression shows the logic between inputs A and B to output, like Y equals A plus B, X or A bar plus B bar. Next is timing diagram. In waveforms, the lower level indicates 0 and higher level indicates 1. We write the truth table according to the waveforms. The truth table gives the functionality of the respective gate. The logic diagrams also help us in defining the functionality. The basic gates have particular shapes that define particular functionality. If there are multiple gates of same type, as in ICs, we have codes to identify the particular IC. Let's see how different gates are with respect to shapes and number of inputs. We will see basic gates, or universal gates. We have a gate with only one input called as NOT gate. NOT gate's symbol has a triangle with a bubble at the output end. The functionality of this gate is inverting. Second one is AND gate with two inputs. The symbol has D shape. The functionality is logical multiplication of the inputs. Next one is OR gate. The shape is kind of mixture of crescent moon and triangle. Curved input end with pointed output end. The gate logically adds the inputs. We have a special gate called XOR gate, also known as exclusive OR gate. The symbol is similar to OR gate, but with an extra curved line at the input. NAND gate is the inverse of AND gate. Therefore, the symbol is similar to AND gate, with a bubble to indicate the inverse. Same goes for NOR gate and XNOR gate. NOR is the inverse of OR gate, and XNOR is inverse of XOR gate. NAND gate and NOR gate can implement any Boolean function or any other basic logic gate. The basic gates can be of 3 inputs as well. When it comes to numbers, there is always some operations. I mean, we play with numbers and call it mathematics. Similarly, we play with binary digits and call it Boolean algebra. It's a branch of mathematics which deals with 0 and 1. Math has operations like addition, subtraction, multiplication, division, finding percentage, roots, exponents. But in Boolean algebra, we only got addition, subtraction, multiplication, and division. Let's compare how the basic operations are done in mathematics and Boolean algebra. We just need addition and multiplication for now to understand the logical working of gate. In normal addition, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 2. When it comes to binary digits, first 3 combinations are same. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. But 1 plus 1 is 1, because we don't have 2 in binary digits. In mathematical multiplication, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. Boolean multiplication is same as well. We just use a dot to indicate the operation instead of cross. We can analyze few basic concepts from these addition and multiplication. Before that, let's call the binary digits as A, which means when I use A, it can be either 0 or 1. Let's analyze for addition with 0. If you observe the first 2 cases here, the first variable is fixed to 0 in both cases. Second variable is A, where a is 0 in first case and 1 in second case. When we are adding 0 with a, the output is also a, so we can say a plus 0 equals a. Let's see for addition with 1. Similar to first two cases, first variable is fixed to 1 and second variable is a, where a is 0 in third case and 1 in fourth case. The output is 1 in both the cases. Therefore, a plus 1 equals 1. When it comes to multiplication, it's simpler because binary multiplication is same as normal multiplication. A and 0 is 0 because anything multiplied with 0 is 0. Similarly, a and 1 is a because anything multiplied with 1 is itself. You can verify here. The first two cases are for a and 0. The second two cases are for a and 1. Another basic concept is inverse, which is also the functionality of NOT gate. Inverse is nothing but opposite. Since we have two level, the inverse of 1 is 0, and the inverse of 0 is 1. If a is a variable, then its inverse is represented by a bar. This is it for today. We will learn about each gate in the upcoming videos. If you got any suggestions or feedback, you can use comment section. Don't forget to subscribe and share the video.